Voice of the Sea, learning from experts across the ocean.
Welcome to Voice of the Sea. In this episode, Kanisa meets one of Hawaii's most respected surf forecasters, Pat Caldwell. Pat has been predicting ocean conditions in Hawaii for 30 years. He explains his job, what a wave is, and how he forecasts the surf. Pat gives us the three most important factors in predicting waves and ocean conditions.
Pat's forecasts provide critical information for your ocean lifestyle, whether you're seeking the flat, calm days of summer or the big waves of the North Shore. I've read your surf forecasts for years, and I'm a big fan. I appreciate so much all of the information that you put out for the public, and I'm really excited to learn how you do your job.
Oh, thanks for the compliments. It's a labor of love. I'm glad to help. My job is with the National Oceanographic Data Center. My background is meteorology. I'm now officially a surf forecaster with the Honolulu National Weather Service. I'm doing specifically the Oahu surf forecast. The other islands can interpolate that information to apply to their beaches.
Surf forecasters are kind of a rare breed. There aren't too many of you. So how do you learn how to do that job?
Through my interest in surfing and weather in high school, I decided to get a degree in meteorology. So I went to Florida State, and so that was my background, was through education and following that dream. And then once I had my education, as I mentioned, they're offhand, I mean, I wasn't out there looking for a job as a surf forecaster. I mean, I would have loved to have, but in reality, they're not advertised every day. Maybe by this day and age, Surfline or some consultants would have that, but there is no such thing as surf forecaster in the Weather Service per se, except for what I do, because it's a special case. The meteorologists over there are specialized. Actually, they typically tend to be well-rounded forecasters. They could be transferred to Kansas tomorrow, and so they need to know all aspects, and so surf would just be one of their many skills. So for me, I have focused all along specifically on learning about forecasting surf.
So can you take me through what you would do on any given day to predict the surf?
Oh, sure. This is an opportune time to do that because being early February, the weather patterns are quite active. We're in midwinter in the North Pacific, and there's lots of systems to look at. And so basically, just as a general thing, the three most important things to remember when it comes to doing the surf forecast is first the generation, and that's basically studying the wind. And then second is the travel, so that depends on how far away the surf generating system is. And then third, you need to look at the nearshore effects of where you're trying to forecast.
By surf generation, you said the wind.
Right, exactly.
And that's because most surf's actually generated by wind.
Right, the waves that people surf that you think of is gravity waves generated by the wind. To keep that separate from tsunamis, which are also gravity waves, but they're generated by movements of the seafloor.
What do you mean by a gravity wave?
Gravity waves means that the driving physical force that keeps that motion going is gravity, because what you have is an imbalance. You have a trough and you have a ridge on top of the sea surface. It's the same thing as the same force that makes a ball roll down a hill makes a wave move through the ocean. The most critical for preparing a surf forecast is that the person understands the great circle roots. We live on a sphere, planet Earth, and when waves are generated, when they travel through the ocean, they do not carry mass with them. It's only the energy being propagated. You can see that individual water particles do move when a wave goes by. They go up, they go over, they go down, and they go back, so they end up creating a circle of movement, each one of those particles. And that circle is greatest near the surface, and it gets smaller as you go deeper. When you have wind moving, and air does have mass, or if you have water moving, such as ocean currents, then the rotation of the Earth causes an apparent movement of moving the mass towards the right of its path in the northern hemisphere. That's called the Coriolis force. But within waves, since there is no mass moving, you do not have the influence of the Coriolis force. So once a wave is generated and starts to travel, it's going to follow the what's called the Great Circle route, and that's just the shortest distance between two points on a sphere. So if you had a string, here's the Hawaiian Islands, here's Japan, and the Great Circle route would be that closest line between 2 points on the sphere. So say, for instance, we're trying to forecast for the Pipeline Pro. So we look at the weather charts and try to find winds that are aimed along the Great Circle route, parallel to that Great Circle route relative to Hawaii. And so sitting there at Pipeline on the beach, if you look out to your far left along the seashore, you'll see kind of point way off to your left. And you know nothing's going to be coming from beyond that, because south of that the land would block it. We have another factor too, is if you have Kauai to the west-northwest of there, and the shadow line from Kilauea on the north side of Kauai to Pipeline is roughly 295 degrees. So you're really wanting to study the compass from degrees 295 up all the way towards the north. And so basically you're looking out towards the source region in the area between 295 to 360 degrees from Pipeline. And that's the Northwest Pacific up to the Aleutians. The magnitude of the waves that are generated depends on three factors. Number one is the wind speed, but then number two is the area over which the wind blows from a common direction. And then number three is how long it blows. Mm-hmm. And that area over which it blows is referred to as fetch, which is typically, the way one defines it is if you have a weather chart and you see the flow going around a low pressure, the wind goes counterclockwise around a low pressure, you look for winds that are parallel to the Great Circle route relative to your target. And then you just draw a box around all those winds parallel to your Great Circle route. And I could show you an example.
Yes, please.
We can see right here in the middle of the plot is Hawaii. And you have two sets of lines. You have these circular lines, and then you have these lines radiating out. And the former lines with the circle, the bullseye, this is travel time for energy that's in the 14-second wave band. So that's roughly 1 day away from Hawaii. That's roughly 2 days. That's roughly 3, 4, 5.
You're watching Voice of the Sea.
And typically the ideal pipeline swell is between 300 to 310. It likes that west component, but as you go to west, then you get the blocking factor from Kauai.
Sure.
So right here around 300 is the ideal spot. So that's the job of the forecaster, is to define those fetches. And then the next things you have to think about are the number one important aspect is the wind speed itself. And in order to get the bigger waves, you need stronger winds. And for any given wind, there's a maximum height that waves can get. Say, for instance, you have 30 knots of wind, and it's blowing from California to Hawaii. It doesn't matter how long, and say it's blowing for 5 weeks. I mean, that's actually can happen sometimes. You can have 25 to 30 knot winds from strong trades over thousands of nautical miles. But waves can only get so big, say the winds are 25 knots, just for this example. Waves can only get so big with 25 knots. No matter how far they blow, for how long they blow, the waves are only going to be around 13 feet. That's about as big as they're going to get.
I didn't
no
realize
matter
that.
what. There's a limit on how big waves can get for any given wind.
Sure.
And so then when we move into these winter type low pressure systems that can get gales all the way up to hurricane force winds, what the forecaster is doing is they're looking for a representative wind to make the forecast with. It may not be the strongest wind, but it's the one representing a larger area. And it's just scientists are always trying to simplify the problem. It's just one way of simplifying the problem. You try to find that representative wind. And for this one, a good one would be what we would call 45 knots,
Okay.
which is pretty close to a storm force winds. There were actually some hurricane force winds with it, but just to be a representative value. So then what are the characteristics of fetch length and duration that you need for 45 knots? I mean, the ultimate that the waves it can get, if they blow 45 knots, say they blew from Japan all the way to California for weeks on end, they would only get so big. And in that case, it would be somewhere right around 50 feet. That would be the maximum they would ever get. And when I use numbers in the world of waves out in the open ocean, keep in mind that there's a spread. You have some 50. That's just your, statistically speaking, the high average of the highest 1/3. There's some waves at any given moment that are bigger than that, and there's a lot of waves that are smaller than that. But we're talking statistics. And so for those that are mariners, and then they say there's 50-foot waves, there is the occasion where you can get a wave twice as big as the significant wave height, say 50 in this case, and that would be what's called the rogue wave. And that rogue wave is just a statistical chance that's typically associated in the generation zone where all the waves are combining. And since waves are additive, if you have several waves from different directions that all merge at the same point at the same time, the waves are additive. And the height of a wave, as we're going to talk about later, is the distance from trough to crest. And the troughs can also be additive if you had a whole bunch of negatives. So if you happen to have a whole bunch of positives and a whole bunch of negatives right next to each other, the distance from the trough to crest can suddenly be twice your typical wave height. And that's what's called a rogue wave.
And rogue waves can be dangerous for large boats out at sea, is
Oh
that
yeah,
correct?
oh yeah. So like I mentioned on this particular case, as using that 45 knot wind as my guideline, you could have 50-foot seas. That means you could have the rogue wave could be 100 feet.
Wow.
And so it's just a statistical chance. It wouldn't happen on every storm, but it's a statistical chance.
So as a surf forecaster, you wouldn't be surprised to see that anomaly, that large rogue wave, 100 feet in the middle of a storm that has 50-foot waves.
Right. That would be something that a mariner would have to consider. But in order to get that 50 feet, there is a distance over which they must blow and a duration over which they must blow in order to build up to 50 feet. And it just so happens to be, in this sort of case, it's right about 1,500 nautical miles. A duration, you would need it to blow roughly 2.5 days. And it's difficult for Mother Nature to do that. This is about as broad as a weather pattern can get. They don't get any bigger than this. I mean, this is midwinter, as broad as a gyre can get for a given low pressure, which is on the order 700 to maybe 1,000 nautical mile fetch, but that's the utmost limit. And so it did get quite, we ended up getting Waimea Bay type breakers, but we didn't get eddy type size limit value.
And
the
by
reason
eddy,
being
you mean the eddy contest?
the eddy ICAL contest, which they require typically your Waimea buoy reading when you get the breakers for eddy contest is running 20 feet 20 seconds. And on this past Monday, when this episode peaked, I think the highest reading was 13 feet 17 seconds. So it was well down below the eddy caliber. And the reason being was first off, it didn't have quite a long of a captured fetch, and then second off, it had a long travel distance.
I see.
And the eddies ones typically have that long captured fetch, and then the head of the fetch reaches much closer, so the decay during travel is less. So that was where I start my forecast. I want to know how big will they grow, and at that point I'm ready for step 2, because I mentioned there's 3 steps. So step 1 is the generation, how big will it grow. So step 2 of a forecast is travel time, and you typically use the aspects of wave period to estimate travel time, and that's because the longer the wave, the faster it travels.
Can you explain that to me? It sounds counterintuitive.
The one good example is to think of the tsunami, and we know that we've always heard that in deep water a fisherman may not even know a tsunami goes past.
Right.
Because it doesn't start to jack up until it feels the bottom. And the same thing with ocean waves. But the thing with wave period is proportional to wavelength. The longer the wavelength, the longer the wave period. Mm-hmm. The wavelength associated with 20-second intervals is like 2,000 feet from crest to crest.
Oh, wow.
In deep water, it's 2,000 feet. So that's pretty close to a half a mile. So it's a long distance over which the energy is spread. Just think of long wavelength, think of people with long legs. You could have me standing next to Wilt Chamberlain, and we both take 3 steps and see who goes the farthest. And so the same thing, you generate all these waves, and inside that big batch of C's, you have short waves, medium waves, long waves, and then you say go. And Wilt Chamberlain and all the long waves race ahead because they travel faster.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG has been providing quality educational programs and services for over 40 years, serving students, teachers, parents, educators, and experts around the world and here in Hawaii. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
Welcome back to Voice of the Sea. Surf forecaster Pat Caldwell explains the factor we've been waiting for. What happens when waves hit the shore?
Many times you can be quite surprised how much low, long period energy can turn into big waves. And that'll be all about part 3 of the forecast. So I mentioned there's 3 parts: the generation, the travel, and then number 3 is when the waves feel the bottom. And so that's greatly dependent on location, the shape of the seafloor, and orientation of the coast, etc. Drop a rock in a pond and you see the nature how waves work. The energy's formed and they travel, but it's not just unidirectional. Even with weather systems like this, there's a lot of directional spreading. So when these waves are created, they're spreading out along this great circle line, but they're also spreading out on great circle lines as much as 45 degrees to either side of that. And during that aspect of spreading and direction, you get loss of size.
Why?
And that's because you're taking a massive, just think of it as a bulge of energy, could even just be one individual wave. Just think of this bulge of energy and it gets pushed out like a Play-Doh being pushed down. It's getting spread out, spreading yourself thin. The last thing we want to talk about is the near shore aspects. And that's the transition from deep water swell into breakers. Water depth is greater than 1/2 the wavelength is called a deep water wave. But so say as the seafloor comes up closer to the coast, as you get into here, these waves, the water here's 1/2 the wavelength, so 1/2 the wavelength, it starts to feel the bottom. So that's the defining issue for whether it would be deep water or shallow. And so once the waves do get into the shallow, we have to consider the aspects of friction. So as for instance, we had a buoy right here, say the buoy's right here, as the wave approaches it goes up, and then as the wave passes it goes down, and it basically forms a circle as it goes, as each wave goes by. And in the ocean going down towards the seafloor, you would have these circles, but they would get smaller and smaller and smaller, and then when you got to a point that was 1/2 the wavelength, they would disappear. Tsunamis, they have sensors on the bottom of the ocean, because the tsunami wavelengths are on the orders of, tens to hundreds of miles, and so the tsunami is actually a shallow water wave, even in the deep water. And so that's why there can be sensors on the bottom that can measure tsunamis going by, and they're out since the 2004 tsunami in the Indian Ocean, there's a huge network in both the Indian and Pacific Ocean, tsunami meters, they're called. So what happens when you go from a deep water wave to a shallow water wave is the wave characteristics change. The first thing that drops is the size, because as the friction eats away at the wave energy, the size is going to drop. And a good example of that is off the east coast of the USA. For instance, I started surfing in South Carolina. So you can have 15 to 20 foot seas out there in the Gulf Stream aimed right at the coast of South Carolina. But by the time those waves travel across that shelf, you end up with like 3 or 4 feet of wave.
In contrast to what we see here in Hawaii, where we have really deep water right off the shelf.
Exactly. So we don't have that aspect of loss of energy by friction. So that's it for surfers. That's one of the reasons that makes Hawaii ideal for big wave surfing. Is you don't have that loss. And surf reports are always given as a range. And as I mentioned, surfers always emphasize the smaller percent of bigger waves because that's what they want to ride. And so how this works is you really have to think of statistical distribution. Say, for instance, if you had a gymnasium full of people, and you took the height of all the people in the gymnasium. This would be what's called the bell curve, where it's got your classic Gaussian. This would be the most average height, I don't know, 5'7", 5'6", whatever, if you had boys and girls. And here would be the real tall ones, and here would be the real short ones. But if you had a big room full, that you would end up basically a statistic. So that's how height of humans tends to be mapped in statistics. But if you go out there and with a yardstick measure every single wave that breaks, right, its moment of breaking, you measure all of them and then you plot them. So this would be the number of waves right here. Like this would be the number of people. This would be 85 people were 5'7", and only 4 were 6'8", or 6'3". But here's the number of waves. And here's what, when you do waves, what they look like. It has this long tail. And so right here would be your most frequent.
Like your 5-footers.
And so on any given day, your most frequent wave would be right here. This would be your average wave height, would be somewhat bigger. And then right over here would be your H1/3. This is what a buoy would measure. The buoy measures the average of the highest 1/3. And then somewhere right about here would be your H1/10, which is the average of your highest 1/10. 100 waves came in, you take the 10 biggest, what's the average of those 10?
Gotcha.
So that's the H1/10. And then somewhat up here would be your H100th, 1 over 100. And then way at the very end would be your H max. That would be the biggest possible wave. And because of this characteristic, so I mentioned surfers are emphasizing the smaller percent of bigger waves. So this is the group that a surf report, they would call it 4 to 6 today. Your 4 is your H1/3,
Gotcha.
and your 6 are roughly your H1/10. And the surfers always talk about the cleanup sets. And those are the waves they never catch because, as I mentioned, the bigger the wave, the deeper the water, the further out it breaks. So the surfers don't sit there and the waves come in and mow them over. So this is your cleanup right here. Is roughly your H100th.
Thanks for watching Voice of the Sea. Exploring Our Fluid Earth is a dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group, teaching ocean science concepts through the disciplines of physics, chemistry, biology, and ecology. Exploring Our Fluid Earth is now available freely online. Find out more at exploringourfluidearth.org.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community from elementary to graduate students. Hawaii Sea Grant.